In the modern world, effective communication is crucial for the success of any organization. The productivity, conflict levels, and overall atmosphere within a team depend heavily on how well information exchange processes are established among employees. But what exactly is effective communication? Let's delve deeper into this topic. Experts have conducted extensive research, examining various perspectives and analyzing real-world examples. The results of this study will help us understand how to foster effective team interaction and avoid common mistakes. Effective communication is more than just the ability to speak. It's a comprehensive set of skills that includes active listening, the capacity to understand others, and the ability to clearly articulate one's thoughts. Space telescopes like Hubble and James Webb have enabled astronomers to peer into the most distant corners of the universe, discovering objects that formed shortly after the Big Bang. As of this writing, the oldest and most distant confirmed galaxy is GSC 13, observed as it was just 325 million years after the Big Bang. However, despite its ancient age, this galaxy is not a pristine object. Analysis of its chemical composition indicates the presence of stars that evolved from a previous generation, one that has yet to be observed. Scientists believe the universe's first stars differed significantly from modern ones. They were enormous, exceptionally bright, and short-lived, perishing in explosions unlike any seen today. Studying these stars is a primary goal of modern astrophysics, as they played a pivotal role in the subsequent evolution of the universe. This discussion will explore what is known and unknown about the universe's first stars, potentially transforming our understanding of the cosmos. In astronomy, all elements heavier than helium, including carbon, oxygen, and iron, are referred to as metals. This terminology stems from the fact that hydrogen and helium were the primary elements in the early universe, emerging after the epoch of recombination following the Big Bang. These two elements still constitute approximately 99% of all matter in the universe today. Other elements formed later through nuclear fusion within stars, supernova explosions, and collisions of white dwarfs and neutron stars. These processes continue to this day, increasing the proportion of metals in the universe. Stars synthesize new elements in their cores and then disperse them into space through explosions, enriching the environment for the formation of new stellar generations. A star's metallicity is a crucial parameter used to classify it and determine its age. Astronomers analyze stellar spectra to measure the concentration of metals and, based on this data, assign stars to specific stellar populations. All known stars in the universe are divided into two main populations. Population 1 stars, which include our Sun, are metal-rich, relatively young, and often host planetary systems. Population 2 stars, conversely, are metal-poor and formed earlier than Population 1 stars. Today, they are primarily represented by old red dwarfs, stars with extremely long lifespans. Larger and brighter second-generation stars have long since evolved into white dwarfs and neutron stars, leaving behind gas and dust clouds from which Population 1 stars subsequently formed. Within the Milky Way, both types of stars can be found. Young Population 1 stars are concentrated in the galaxy's spiral arms, while older Population 2 stars reside in the galactic halo, globular clusters, and the galactic center. Of particular interest is the oldest known star in the universe, located within our galaxy and known as HD 140283, or the Methuselah star. It is situated just 190 light-years from Earth in the constellation Libra and is currently in the early stages of transforming into a red giant. Methuselah's age has long been a subject of debate, as estimates derived from various methods yielded values around 14.5 billion years, which exceeded the age of the universe itself. However, recent studies have somewhat lowered this estimate. In 2021, stellar evolution modeling constrained its age to 12 billion years, which aligns better with the age of the universe. The story of the Methuselah star warrants special attention, as its metallicity is 250 times lower than that of our Sun. Imagine a cosmic object composed predominantly of hydrogen and helium, with only trace amounts of heavier elements. Herein lies the most intriguing aspect. Even such a minuscule quantity of metals indicates that this star formed from matter left behind after the life and death of other, more ancient stars. These pioneering stars could have introduced the first elements heavier than helium into the universe, the very elements that make up everything around us, including ourselves. Scientists have even hypothesized the existence of a so-called population 3, stars born from absolutely pure, pristine gas, untouched by metals. These are considered the very first luminaries of our universe. Interestingly, the numbering of stellar populations is in reverse order relative to their appearance. This is because metallicity was initially measured in relatively younger stars, such as our Sun. The question of precisely when the first star ignited in the universe remains open. Theoretically, this should have occurred after the epoch of recombination, when hydrogen and helium atoms formed, approximately 380,000 years after the Big Bang. The search for these first stars focuses on the period up to 400 million years after the Big Bang, when already formed galaxies are observed. However, events in such an early universe are currently inaccessible for detailed study, and according to Astronomy magazine, even future generations of telescopes may not be able to penetrate this epoch. Yet, there's no need to despair, as certain prospects exist, which will be discussed later. It is known that the gas filling the early universe consisted of 75% hydrogen and its isotope, deuterium. The remaining quarter was helium and its isotopes. Lithium and beryllium were also present in minuscule quantities, their concentrations estimated at 1/1000th of the total existing matter. Computer models reveal that the cosmic microwave background (CMB) map holds crucial information. Slight temperature fluctuations, depicted by color, indicate tiny variations in the density of matter in the early universe. These very variations served as the starting point for the formation of vast clouds of primordial gas. Without these minute inhomogeneities in plasma density, the universe would have been uniform, filled with a sparse cloud of hydrogen and helium. However, due to gravity, these fluctuations transformed into regions of concentrated matter, enormous gas clouds surrounded by dark matter halos, which began to contract under gravitational pull. However, this does not mean that stars immediately began to form from these clouds. The process proved to be far more complex. The matter in space was still quite warm, and due to the absence of heavier elements, there was no efficient mechanism to cool the gas down to the temperature required to initiate nuclear fusion. Paradoxically, a gas cloud from which a star is meant to be born must be extremely cold, no warmer than 10 Kelvin, or -263 degrees Celsius. During the gravitational compression of a cloud, gas particles collide more frequently, causing them to heat up. Heated atoms move too rapidly, and gravity cannot force them to contract further. Consequently, gravity fails to overcome the internal thermal pressure, and the cloud's collapse ceases. The situation was further complicated by the absence of nearby exploding supernovae, which could have compressed the gas with their shock waves. The only way to alleviate the excess pressure was to cool the gas. But how could this be achieved in space, where there are no temperature differences or cooling agents? The only way for primordial clouds to lose energy was to radiate it as photons. Modern molecular clouds efficiently dissipate heat due to the presence of complex chemical elements. Heavy elements can emit energy through various ionizations and changes in electron energy levels, while molecules do so through vibrations and rotations. The first stars lacked this luxury. Simple hydrogen atoms are limited in the amount of energy they can radiate. Therefore, cooling through energy loss by basic hydrogen and helium atoms was slow and difficult. Fortunately, in the early universe, which was smaller than it is today, gas clouds were denser and more massive. High pressure within these clouds forced some atoms to combine into molecules, and molecules, as known, are better energy radiators. This led to a decrease in temperature, allowing clumps of matter within the clouds to contract more strongly. According to computer modeling, gravitational compression capable of overcoming the internal pressure of atoms with insufficient cooling required a significantly greater cloud mass than, for example, the cloud that spawned our Sun. Only colossal clouds could undergo collapse under such conditions. Importantly, during this compression, the matter did not fragment into separate pieces, leading to the formation of a single, truly gigantic star from each cloud. This is why scientists hypothesize that the first stars were enormous, with masses estimated from several hundred to 1,000 solar masses. These blue titans likely shone millions of times brighter than the Sun. Further supporting this hypothesis is the fact that no representatives of the so-called population 3, the very first stars, have been detected to date. If any of them were dwarfs, they could still exist today, given that red dwarfs have lifespans measured in billions, or even trillions of years. Astronomers believe that no red dwarf star has yet ceased to exist throughout the universe's history. In contrast, the greater a star's mass, the shorter its life cycle. Giant stars must maintain high thermal pressure to counteract gravity, which accelerates thermonuclear reactions and, consequently, fuel consumption. It is probable that the giant population 3 stars existed for only 2 to 5 million years, or even less. On cosmic scales, they barely had time to flash before transforming into supernovae. It's no wonder we haven't been able to observe them directly yet. After their birth, gravitational attraction caused these stars to draw closer. Astronomers believe this process took several hundred million years but ultimately led to the formation of the first galaxies, illuminating the universe. Beyond their colossal mass and size, the first stars likely possessed extremely high temperatures, 15 to 20 times hotter than the Sun, and shone a million times brighter. Undeniably, such characteristics led to immensely powerful energy emission, predominantly in the ultraviolet range. Scientists hypothesize that this radiation was the primary cause of the ionization of neutral hydrogen in the early universe. The opaque fog of neutral hydrogen began to be permeated by transparent pockets of ionized hydrogen, which gradually expanded, revealing a universe where radiation propagates unimpeded. The unusual first stars of the universe, having lived short lives, also met atypical ends. Today, it is known that stars with masses exceeding 10 solar masses conclude their existence with a spectacular supernova explosion. However, population 3 stars, possessing much greater masses, were expected to explode as a special type of supernova. According to physical calculations, stars with masses between 140 and 260 solar masses form so-called parainstability supernovae at the end of their lives, leaving behind neither black holes nor neutron stars after the explosion. This occurs because massive, hot stars function as powerful thermonuclear reactors. The energy generated in their core is emitted as high-energy photons, specifically gamma rays. In the most massive stars, it is the pressure from this gamma radiation that ensures stability, counteracting gravity's attempt to compress the star's outer layers towards the core. Consequently, even a partial reduction in gamma photon pressure disrupts this equilibrium, and the star begins to collapse inward. As gamma rays travel outward from the star's core, they constantly interact with free atomic nuclei and electrons, and also collide with each other. One outcome of these interactions can be the creation of particle-antiparticle pairs, such as electrons and positrons. When matter and antimatter collide, they annihilate, again forming a high-energy photon. These photons also interact with surrounding particles, maintaining the very photon pressure that ensures the star's stability. However, when a star becomes so massive and hot, more and more gamma rays are produced within it, and increasingly more are absorbed to create electron-positron pairs. At a certain point, this process can outpace annihilation, disrupting the equilibrium. More photons are absorbed by electron-positron pairs instead of generating photon pressure and maintaining the star's stability. The reduction in photon pressure allows gravity to temporarily gain the upper hand, compressing the star more intensely. This, in turn, leads to an even greater increase in core temperature and energy production, meaning even more gamma rays are created, which collide more frequently, forming even more electron-positron pairs that absorb even more photons. As a result, the core becomes unstable in an unstoppable process. The core disintegrates, and temperature and pressure rise so dramatically that all remaining hydrogen ignites in mere seconds, triggering a thermonuclear explosion of incredible power. The star is torn apart, leaving behind neither a neutron star nor a black hole. Such cataclysms present a unique opportunity for the dissemination of heavy elements, forged within stellar interiors, throughout the universe. At the moment of a star's demise, all elements synthesized during thermonuclear reactions, up to iron, are ejected into space. Thus, the conclusion of these stars' life cycles was as crucial as their birth. It is important to emphasize that only stars with negligible metal content can explode as parent-stability supernovae, provided their mass falls within the range of 140 to 260 solar masses. However, according to recent research, the first stars could have exceeded the Sun's mass by 1,000 times, significantly surpassing the threshold for parent-stability supernovae. Scientists calculate that the explosion of such a hypernova should lead to the formation of an intermediate-mass black hole. The study's authors propose that these black holes could have been the starting point for the formation of supermassive black holes. Gradually merging with each other, they increased their mass and transformed into the giants that reside in galactic centers today. Thus, the first stars profoundly influenced the subsequent evolution of the cosmos, enriching the early universe with chemical elements that later became the building blocks for modern stars, planets, and ultimately, for the emergence of complex life forms, including ourselves. It is no surprise that scientists are determined to observe such a star and study its characteristics. One of the most fascinating aspects of physics is the finite speed of light and its associated effects. This circumstance allows us to observe stars that have long since ceased to exist, but whose light continues its journey towards us. Numerous attempts are currently underway to detect these stars or at least traces of their impact on the surrounding environment. In a recently published scientific paper, a group of astronomers hypothesized that third-generation stars could have formed later, even after the formation of galaxies that already contained stars with a certain amount of metals. Isolated regions of pristine gas might have existed in the early universe, which, upon collapsing, gave birth to stars devoid of heavy elements. Such pockets of primordial matter could have surrounded ancient galaxies, suggesting the need to search for population 3 stars and galactic halos. Within this framework, astronomers conducted a study of the well-known galaxy GNZ11, which until recently was considered the most distant known galaxy. Using a spectrograph on a new space telescope, an interesting region near the galaxy was discovered, showing no traces of heavy elements, but a distinct signal from hot, ionized helium. The question arises, what could have ionized helium in a metal-free gas cloud near an ancient galaxy? One possible explanation is the presence of an active black hole at the galaxy's center, whose radiation could ionize the helium. However, the galaxy is at a considerable distance, and the gas temperature does not align with this scenario. Therefore, the study's authors propose that the ionization could have been caused by elusive population 3 stars, whose mass exceeds that of the Sun by approximately 500 times. Although the data obtained are insufficient for definitive confirmation of the discovery of first-generation stars, further research using the James Webb Space Telescope may provide compelling evidence supporting this hypothesis. However, direct observation of the first stars would require a telescope with a mirror diameter of approximately 100 meters, operating in the infrared spectrum and shielded from the thermal radiation of the Sun, Earth, and Moon, similar to the James Webb Telescope. Nevertheless, astronomers remain hopeful, believing that individual stars might be detected through gravitational lensing, where a massive galaxy cluster creates a natural lens in the opportune location. This method has already been successfully applied in the search for the most distant galaxies. Perhaps the bright flashes from these stars' explosions will also become visible to us. In any case, astronomers are confident they will overcome the final observational frontier, possibly even in the near future.